خب ببین بچه من الان نظرسنجی بذاریم. یه ایده اینه که من این دکتر رو آنها بگیرم و اینا رو فکر کنیم.
Okay, so let me okay, you notice that the speaker is different from me. That's my PhD student. I asked her to do this because she has kindly provided me with these slides in short notice. In the chaos that is here, I lost my file, so I'm gonna combine my lecture from 2 sets of slides and a few screen captures from various sources that I have stolen from. So.
Okay. So shall we start then? If everyone's ready. Sure. Okay, so it's a pleasure to me to welcome everyone to the second day, to the afternoon session of today. So our first speaker today is Ali Rajaei from Tarbiyat Modaris University, and he'll talk about some small class number problems.
Thank you. So let me thank the organizers, especially Ilhan, and on the side of IPM, I know that Hadi and Esmail were very involved with this, so I thank them all. And today I'm gonna speak on a work in progress. I'm gonna report on the work that my PhD student Farahnaz Amiri, whose name you see here, has done. And well, let's start. Okay, so these are the topics that I will probably spend some time on today. So first, I have to describe what I mean by small class number problem. For example, I'm gonna tell you about the history of class number one problem that dates back to Gauss. And then I'm gonna follow the historical development of the problem, go to Dirichlet and the work of Higner and Stark. And then I'm gonna talk about the generalization of this problem. So here you see class number one problem for complex multiplication number field. And then discuss some general techniques for solving class number one problem for complex multiplication number fields. Okay, so as I told you, I've lost my file, so I have to take some time to bring some image captures. So these are some copyright violations, and the first set of copyright violations would be in order to describe Gauss's class number one problem. I didn't see any better place than to go to Ilan Rosen's book, because I think it has a very poetic description of what happened. So I hope you see this. Okay. So, well, so we are talking about Gauss's masterpiece, Disquisitiones Arithmetica, and in article 303, Gauss is talking about the results he has about definite quadratic forms. Now, what he describes about definite quadratic forms can be interpreted as calculations of class numbers. You have to remember that at the time of Gauss, there was no formal notion of group or ring or ideal. So all that Gauss was doing was some computation with quadratic forms. And okay, so first I'm going to talk, so the history is divided into two parts. according as the quadratic fields we are talking about have negative discriminant or positive discriminant. Okay, so I hope taking this. Do you see the? I'm not sure whether you see the whole picture or you see the videos of people here too. Okay. So if there's a problem viewing the file that I'm sharing, please let me know. Do you see the number 427 here?
Yes, we see, and we also see
Okay.
your cursor moving around. Yes.
Okay. All right. Okay. So what Gauss observed is that apparently the class number of these imaginary quadratic fields as the discriminant goes to infinity. I mean the absolute of the discriminant, because the discriminant I'm assuming is negative. The class number goes to infinity. So what he has recorded is that the last number for which the class number is 1 in Gauss's recording has to be negative 163, and the last one that he records as having class number 2 is negative 427, and the last for which the class number is 3 is negative 907. So these are some examples of small class number calculations. So on the face of it, the problem is divided into two parts. One is that, if d goes to infinity, absolute of d goes to infinity, whether h of d goes to infinity or not. In other words, of any given number, there are only finitely many imaginary quadratic fields of that class number. Then the second problem is how to effectively compute this. For example, if you know how many, if you know that there are finitely many imaginary quadratic fields of class number 1, then the second problem is just list them. And in order to before I go to the history, what I want to talk about in Farahnaz Amiri's work is that we have chosen some number fields whose Galois group, instead of Z2, which is the case for negative imaginary quadratic fields, is their class number is S4. I'm sorry, the Galois group is S4, and we want to list all of them that have class number 1. So that's eventually what I'm getting at. Now, in order to reach that, I want to just go over the history. I think it's nice to go over the history, and I guess Farahnaz did not agree with that because she didn't put it in the slides. But in any case, I want to go I want to take 15 minutes to go over the history, because I think the history is really nice for this problem. So unfortunately, I have to stop share and then share the new image. Sorry for losing my file. I have to go through this. I don't know any better way to do this. So the first development came with Hecke, 1918. So again, we are talking about negative discriminants. Oops. And what Hecke was able to show was that assuming the GRH, generalized Riemann hypothesis, then there is an absolute constant C such that the class number of the imaginary quadratic field with discriminant D is greater than this constant times square root of absolute of D divided by log absolute of D. So as absolute of D goes to infinity, that shows that the class number the class number goes to infinity. So it solves the first problem, but assuming generalized Riemann hypothesis. I'm sorry, I couldn't fit all of them into one onto one PDF because I just lost the file and like 20 minutes to my talk, and I hope it works this way. As I told you, it's better not to record this. I can't find the share. Okay, I think I found it. Am I still connected? Can you hear me?
We hear you, but we don't see. You have not shared any.
Let me close all the stuff. So I don't know what has happened, but okay. Somehow my screen share doesn't work. Okay, let me relaunch it again. Okay. Okay. So we had seen that Hecke showed that if GRH is true, then the class number goes to infinity as absolute of D goes to infinity. Now the next development was that Doering showed that if Riemann hypothesis is false, then the class number is greater than 1 as D goes to infinity. In other words, if D is sufficiently large, then H of D is greater than 1. So that shows that there are finitely many of class number 1. Do you see the slide? Do you see Mordell and Heilbronn in the
Yes,
slide?
we see from Doering down to Heilbronn. Yeah.
Right. Sorry about these problems. Next, Mordell showed that if Riemann hypothesis is false, then HD indeed goes to infinity as D goes to infinity, absolute of D. So it's just not class number 1, but the growth that we expected. Then Heilbronn showed that if GRH is false, then H of D goes to infinity as absolute of D goes to infinity. So that shows that solves the problem of that there are finitely many imaginary quadratic fields with a given class number, but it shows it very strangely. So let me bring the next slide. Sorry about these interruptions. Okay. So this method of proof is really amazing because on the one hand, Hecke showed that if GRH is true, then we get the result. And on the other hand, these 4 people together showed that if GRH is false, we also have the result. So the result is true. And I think this is an amazing proof. Like with or without GRH, you can get what you wanted. Now, Siegel, in the next step, without using Riemann hypothesis, solve the problem. And in 1935, he proved that for any positive epsilon, there is a constant such that h of d is greater than, I mean, the class number of q squared root negative absolute of d is greater than c of epsilon times absolute of d to power a half minus epsilon. But c of epsilon is not effective. So that solves the theoretical part of the question, but does not give you the list. Like if you want to know all number fields with class number 2, for example, all imagine a quadratic field with class number 2, that's not going to help you because c of epsilon is not effective. Then the next important step was taken by Higner, and this is interesting because he kind of related this to modular functions. So this is quite related to Ekin Osman's talk. So what he did was through a construction which now today is known as Higner point constructions, showed that indeed Gauss's list is complete. So -1, -3, -4. I mean, sorry, -1 is reported as -4 here because we are counting, we are reporting the discriminant. Sorry about that. So q of I, q of square root -3, q of square root -7, and so on. So this would be square root -2, for example. And the last one is -163. Now, there was a small gap in Higner's paper, which people attributed to a problem in one of Weber's papers. But it was fixable. But unfortunately, before this gap was fixed, Higner died. And Stark kind of, Harold Stark kind of solved the problem. So I should also say that before Harold Stark did this in 1967, Baker also found another proof, but his proof was using linear forms in logarithms. So, but I'm not going to talk about such methods. So let me go to the next development. Now, the next development is that Baker and Stark also solved the class number 2 problem. And indeed, Gauss was right. So the largest absolute value of negative discriminant was 427, as Gauss had written. But these methods did not work for the class number 3, the case of class number 3. So the next development is again connected to modular forms and elliptic curves. So I seem to have problem sharing. Oh, okay. I see that I was sharing the wrong slide. Okay, no problem. Okay. Now, what Goldfeld proved in 1976 was that if there is an elliptic curve satisfies the modularity, I mean, the L function of the elliptic curve satisfies the functional equation that now we know due to the work of Wiles. It has an order, has a zero of order 3 at s equal to 1. Then there is an, for any positive epsilon, any given positive epsilon, there is an effectively computable constant such that h of v is greater than c of epsilon times log d, log absolute d to 1 minus epsilon. This. So this is dependent on proving that there is an elliptic curve whose L function has order of vanishing 3 at s equal to 1. Okay. Now, the next funny thing in the theory was that, I mean, you could say that you know much more today, but that was the state of the art at those times. Okay. So what Gross and Zagier did in their paper was that they proved that this curve, maybe I should make it a little bit smaller, maybe too small. Okay. This curve, minus 139 y squared equal to x cubed plus 10x squared minus 20x plus 8, satisfies all that we wanted in Goldberg's, in the hypothesis of Goldberg's theorem, and it has a zero of order exactly 3 at s equal to 1. Now, so that should probably, so remember what we were trying to do was that Stark and Baker methods did not solve the class number 3 problem. So that's why we are going to elliptic curves, and that's what Gross-Zagier did. So they provided us with an elliptic curve. But this elliptic curve has a little big conductor. So if you compute C of epsilon in Goldberg's theorem, it's a bit too large to do the computations for class number 3 problem. Now, Brumer and Kramer showed that this elliptic curve, y squared plus y equals to y squared plus y is equal to x cubed minus 7x plus 6, whose conductor is 5077, has rank 3. Now, if you could show that it was modular, and remember, we are talking about 1986, it's before Wiles' theorem. If we could show that it was modular, then we would have an elliptic curve with a small conductor to do the class number 3 computations for negative quadratic field, for imaginary quadratic fields. Now, assuming that it was modular, Buhler, Gross, and Zagier showed that its L function has a 0 over 3, and Mess and Serre verified that it was a modular curve. So Osterle was able to prove that using this curve, he was able to prove that h of d is greater than 1 over 55 log absolute of d for prime discriminants. And this was enough using results of Montgomery and Weinberger to show that negative 907 indeed was the largest negative discriminant of class number 3. So again, Gauss was right. Sorry for taking this 15 minutes detour, but I think it was an interesting piece of history. Now, going back to my slide. Okay. So we want to know what kind of generalizations can we do for this problem. One nice way to think about this is that you can think of imaginary quadratic fields as simplest complex multiplication number fields. And you wish to find families which, like imaginary quadratic fields, have a finite list of small class numbers. So for example, in contrast to real quadratic fields, we know that it's an open conjecture of Gauss that there are infinitely many such discriminants. In other words, we have infinitely many real quadratic fields of that are PID, have class number 1. So we kind of want to go to families that have finitely many number fields of given size, class number size.
I don't hear you anymore. I guess the connection cut, or is it just me?
I can't hear him either.
Yeah, it looks like he lost his connection, so we have to wait for him to come back,
Yeah.
I believe.
Ah, you're back. I think now you're muted.
Sorry, I'm having too much trouble today. Sorry about that. Maybe I should have canceled and sent you the video. Sorry about that. Okay. In 1974, Odlyzko proved that there are only finitely many normal complex multiplication fields of a given class number. So that means that we are talking about Galois complex multiplication fields. And we want to know what happens to non-Galois such fields. So talking about the list, in 1979, Hofstein proved that normal complex multiplication fields of degrees greater than 436 have a relative class number greater than 1. So one other development was that people started thinking about the subfields of these number fields who had class number 1. And for complex multiplication fields, you have a divisibility of class numbers. So if you have a complex multiplication field that has class number 1, then its subfields should also have a relative class number equal to 1. So that's the good thing about complex multiplication fields. So for example, in Farahnaz's work, the S4 extensions cannot be complex multiplication fields because for one thing, the complex multiplication fields, the complex conjugation should be in the center of the Galois group. And the center of S4 is 1. So if you go and look at S4 extensions of Q that are imaginary, then you don't find any complex multiplication fields among them. This bound, Hofstein's bound, was later improved to 266. And if GRH is true, then actually you need to only go to degree less than 164. Now, then those who were looking at relative class number 1, there were many people, among them Li and Kwon, showed that those who have relative class number 1 and are Galois and are complex multiplication have degree less than 216. And this bound, assuming GRH, can be improved to 96. So degree is less than 96, less or equal to 96. So this was for those who have relative class number 1, and with class number 1, the degree is less than 104. No assumption needed for GRH. The next development was that in 94, Yamamura restricted to the case of abelian CM fields. Can you still hear me?
Yes, we hear you.
Okay, sorry. I hear just strange beeps from the computer, and I have to assume that I'm disconnected. Okay, so among the abelian ones, you have 172 complex multiplication fields, and the degrees are less than 4. Now that was abelian, and you want to think about non-abelian ones. Among the non-abelian ones, degree 8 was done by Lubotin and Okazaki. Degree 12, and again by Lubotin, Okazaki, and Olivier. And again, 2 papers by Lubotin and Okazaki, the case of 16. Now, the case of simplest non-abelian Galois groups, which is the dihedral case. For them, the case of degree 4p, where p is a prime greater than 3, was done by Lubotin and Lefebvre and Lubotin and Lefebvre. So there are 3 papers that do these cases. Now, it seems I have just 20 minutes left, so maybe I skip part of the history. So for the case of 20 and 40, it's the work of Park. And the case of 32 by Park, Young, and Kwon. 36, 48. And the list was complete in 2006 for the degree 64 and 96. Okay, so the reason Farahnaz is working on S4 is that this is not a complex multiplication field, so we want to know whether we can do anything about that. Okay, before I continue with this, I just want to explain how this problem grew. Well, the reason Farahnaz was working on this problem was that, as you noticed when I was talking about Gauss's problem, the discriminant was either a prime or 4 times a prime. In other words, we were thinking about q square root negative p a prime. The reason for that is another theory, again due to Gauss, is genus theory. So genus theory tells you that if you look at q square root d, when d has multiple prime factors, so for example, if d has t prime divisors, then I'm talking about q square root d, not the discriminant. What happens is that you have got t minus 1 copies of Z2 in the class group. That's that comes out of genus theory. Did also is that he completely characterized the 2 torsion of the class group for the case of imaginary quadratic fields. So that's why you go and look at just the primes, square root negative of prime. Originally, what I had assigned to Farahnaz was kind of a generalization of Gauss's genus theory. I didn't want her to get involved with this analytic results because I thought that would be too difficult. So I just wanted her to work on the algebraic part. And there was a difference of opinion between me and her. I guess the first difference of opinion that you saw was that she didn't like the historical development I was going to talk about, so she didn't provide the slides to me, and I lost my file, and it was a complete disaster. So, well, I trusted her instincts on this. So that doesn't mean that I'm gonna that doesn't mean that I'm not gonna talk about what I originally assigned to them. So I'm gonna take another 10 minutes to do what I wanted her to do. So I'm gonna show you the work of another student of mine. I guess he's here also, Abbas. I guess he's here. So let me find his slides. So one general problem that I solved today was that if you lose your file, just steal from others. So that's what I'm doing today. Okay. I should stop share. I was sharing, I don't know what, but let's go to Abbas's slides. Okay. Okay, so I should kill the share and then go back to share again. Sorry about this problem. Okay, yeah. So what Abbas did in his thesis was that, so I was interested in, so look at the case of imaginary quadratic fields. We know that if there are a lot of divisors in D for q squared root negative D, then there is a large 2 torsion inside it. Now, we wanted to know what kind of divisibility results can you prove if you know the structure of your Galois group. So we are considering here, for example, one of the results he proved in his thesis. And I should also mention that the reason we worked on non-abelian fields was that there were some results by Hans Zantema from 1982 that treated the case of abelian number fields. So we thought that maybe the simplest non-abelian case is the dihedral case. and the simplest dihedral case. In other words, this DL field is the dihedral group of order 2L, where L is an odd prime. So for this case, assuming the some bound on the ramification, we can prove some divisibility for class group. So if you have an S3 field, you have a non-Galois cubic field, that's L equal to 3. If the discriminant is positive, or it's a pure extension, like it's Q square, cube root of something. That's what we call Q cubic. If the number of ramification is greater than 3, then 3 divides the class group. If the discriminant is less than 0 and K is non-pure, as long as you have more than 2 ramified primes, then 3 against the class number. And it's kind of nice because in the case of quadratics, that's degree 2, genus theory provided you with divisibility by 2, actually much more. Divisibility, I mean, having even talking about the structure of the class group. Like you have T minus 1 copies of Z2 in the class group. Now, in the case of dihedral ones, where L is greater than 3, if the discriminant is positive, and if the number of ramified primes is more than 3, then L divides the class number. And for negative discriminant, as soon as there are more than 2, more or equal to, I mean, more than 1 primes ramified, then L divides the class number. So that's that tells you that if you are looking for small class numbers, then what kind of Galois number fields you should look for. For example, you shouldn't be looking at dihedral ones. Okay. Another result, this result is dependent on total ramification of a prime in your number field. Again, we are assuming that the number field is a dihedral one, the simplest dihedral one, so L is a prime here. If this prime splits in the quadratic subfield, I'm sorry. I had to. Oh, I'm sorry. K is a field of degree L whose Galois closure is a dihedral group. I'm sorry, I made this mistake. Also in the previous one. So L is of degree. So K is of degree L over Q, and its Galois closure is dihedral. So. Sorry, for the previous slide also we had this assumption. So K is of degree L over Q, but it's not Galois. Its Galois closure is a dihedral extension. So if you have this L splitting in the quadratic subfield of the normal closure, or if P is congruent to 1 mod L, then L divides the class number. I like this result because it reminds me of the theorem of Ribet that Ekin Osman referred to. So the case of Ribet theorem, before Ribet, Mazur had done all the primes that are not congruent to 1 mod L. And the case of P congruent to 1 mod L was done by Ribet. That was a major contribution. So I like this result because you have this result appearing there, and you kind of, when you work with, and actually I should tell you that the whole reason I'm interested in this kind of computations is that I want to know what happens when instead of an elliptic curve, you work with number fields. And there are some beautiful set of conjectures by Delaunay who make an analogy between the theory of elliptic curves and the class groups of number fields. So all these results that are done for a class group, basically, if you are able to do a similar construction, or I mean similar, if you use that dictionary, would translate to some results about the Shafarevich-Tate group of the elliptic curve. And that's why I think these problems are interesting, because that's a major problem. And like the case, the reason I reverted back to that history was that for the class number 3, the solution was completely related to elliptic curves and modular forms. And I think these two theories go hand in hand. So that's why I like this. Okay. Now, another philosophical reason I like this is that, well, you have the case of, you have Dirichley's contribution to the theory, because Dirichley introduced, in order to prove that there are infinitely many primes incongruences, so he created the concept of the L function for number fields, and then gave the first class number formula. So, and in the class number formula, you see that the class number is intimately related to the units. And it's a philosophical interpretation that you cannot really separate units from class number. So let me skip a few pages, because I guess we're kind of short of time. There is an exact sequence. There we go. So, so this is the exact sequence that you can find in the work of Zantema I alluded to in 1982. And this is a nice exact sequence, because it tells you, so this co-K is the polya group of K. It's a subgroup of the class group. This is the subgroup that we can easily describe some divisibility results for. So it helps us, because it's a subgroup of the class group. Whenever you prove that a prime divides this subgroup, then you have proof that your class number is big. So in this exact sequence, so you see something about the class group, but you also see something about the units. And it is hidden in this because this is a Galois cohomology, and the coefficients of this cohomology are the units of the number field. So again, you see that the units and the class group are tied together in a nice exact sequence, where the first one, I mean the middle term, is something telling you something about the ramification. So EP is here the ramification index of P. So what Abbas did was that this is an exact sequence for Galois extensions over Q. So he generalized this to a Galois extension of two number fields. So in other words, he relativized this notion. Instead of using Q here, he can put a number field here. The exact sequence is a little bit different, but he has some results about some analog of this polya group, which he calls the relative polya group. Okay. So I was in the original problem I gave Farahnaz was that using a relativized notion of this exact sequence, which was the work of Abbas, my other student, who is now in IP, a postdoc in IPN, was that to use this relativized polya group to see if she can shrink the list of those S4 extensions whose class number is 1. So in other words, I asked her to see if relative considerations can help you to narrow down the list of Galois S4 extensions of Q whose class number is 1. And that was supposed to be a simpler problem than what she has done now. Let me see, I have only 4 minutes. I don't think I can mention much about Farahnaz's work. Let me go back to Farahnaz's slide. So maybe I can share a few of her slides. Okay. And again, I apologize that I had to steal other people's slides. Okay. So so this is what is the upshot of what she has been doing. So I wanted her to focus on the algebraic part, but she has rather focused on the analytic part. And the analytic part is really difficult because it depends on some results regarding Siegel zeros. So if you know some zero-free regions near s equal to 1 for the zeta function, then you know a lot. And that's what Siegel proved. And if Siegel could prove that between, so less than 1, between 0 and 1, whenever you can prove that the zero-free regions are very close to 1, then you can know a lot about discriminants, and you can know a lot about the zeta function. So Siegel zero is a zero of the zeta function that we conjecture that does not exist. But that doesn't mean that we have good control of Siegel zeros. So I leave the analytic part. It's very involved. Let me see what can I say about the algebraic part. We have the relative class number formula, and for complex multiplication, we have divisibility. In the case of Farahnaz, because the S4 extension is not complex multiplication, we don't have any divisibility results for class numbers. However, she's able to prove that the relative class number of two fields, one is a quadratic extension of the other one, can be at most 4. So it's either 1, 2, or 4 if the big field, if the S4 field is has class number 1, and that is the part that uses the results of relative polya group. I guess I can't talk about the Cohen-Lenstra heuristic here. Okay, so there is recent work by Alex Smith. So traditionally, people who talked about Cohen-Lenstra heuristic, they only considered the odd part of the class number, because the two part of the class number is really difficult for the imaginary quadratic fields. apart from genus theory, the rest is difficult. And what recently Alex Smith has shown is that if you kill the genus part of the class group, so if you look at not the two silos subgroups of class group of K is Q squared with negative D. But instead focus on 2 times the class group of K so that the genus part is killed. Then it behaves randomly, according to the general philosophy of Cohen-Lenstra. And I guess we are also studying this to see whether in our problem we can prove a similar result. But that's work in progress, and I guess I better stop here. And my apologies for this mishap. I lost my file and had to go through several files. I didn't even have time to make them into a single PDF. I'm sorry about that. But your torture is over now. Congratulations.
Thank you very much.
Thank you.
So the big war was not with the children, but with technology, it seems.
The children, actually, I gave them the other computer, so probably that one is gone for good.
Okay.
Because I don't hear any noise from them, so they are gaming with the other one. I hope I can have something at the end of the day.
Okay, are there any questions? Yes, there is one. Ehsan Hosseini.
Yes, please go
Hello.
Hi.
I want to say a remark only. Some weeks ago, there was a online seminar that Alex Smith speak about his work, and I talked with him about the polya group, the notion of polya group, and controlling the polya group with his techniques. And he said that it is not immediate in his mind, but by the good local conditions that come from controlling by ramification, he expect that some results can be given by his methods. And I remember that he also writes something in a paper about in front of him about polya group, and I think sometimes later he maybe published something about these things using his techniques. In fact, he defined a good pairing in an abstract manner that works for class groups and Tate-Shafarevich groups, and it seems that well behaved with the restriction manner that happens in the polya group.
Great. Actually, in the case of elliptic curves, oh, you're talking about the work he has done in numbers. It's not the elliptic curves.
Number fields are also elliptic curves. He had also some results about elliptic curves. In fact, he talked about both of them. He defined a pairing that generalizes a pairing by Tate and Casals, maybe, and
Right,
then
right.
using this get some results in Tate-Shafarevich group and class group also.
Right, right. Actually, thank you for mentioning that because I forgot to, I mean, I didn't have time to. So Ehsan is another PhD student of mine, and actually he has defined a dual notion to that of relative Fourier group, which we have unofficially called it the Ostrovsky group, because Polya and Ostrovsky worked on this problem, but somehow people named the group as Polya group. They originally named it Polya Ostrovsky group, but then it was uh, called only Polya group. And the dual notion that Ehsan has defined, which we call the Ostrovsky group, is really an interesting one. And actually, in the generalization from Polya groups to relative Polya groups, what we lose is that Polya groups are not completely controlled by ramification, whereas what Ehsan has defined is completely controlled by ramification. So that's an interesting notion, I guess. Um, uh, with regards to elliptic curves, as you mentioned, Castle's tape pairing, that gives a duality. That's why elliptic curves have, either a square Tate-Shafarevich group or twice a square. And twice the square was the first examples, as far as I know, were given by Poonen, because our characteristic two, there is this ambiguity whether antisymmetric, you also want to be zero on the diagonal or not. So I guess that was a new phenomenon. Before Poonen, people didn't know that the order of a Tate-Shafarevich group can be twice the square. So yeah, I guess Amir has a question if you want to ask your question.
Hi. I have actually two questions. One of them is, people also studied fields with class number 2 or 3, like they have been classified for quadratic imaginary. Have you studied fields with class number 2 here, for example, for other extensions, non-abelian or non-CM, things like that? And my other question is that, have people studied fields with Polya group trivial, like trivial Polya groups, like classify all, say, quadratic imaginary fields with trivial Polya groups?
Yes, regarding the Polya group, that problem has been done because, well, actually, I should also say that Polya group is also the subgroup of class group generated by the factorial ideals. And factorial ideals are Manjul Bhargava's extension of the usual factorial. So he defines them as an ideal, and actually that's the work in his undergrad for which he got a Morgan Prize. Right, so the Polya group is actually the easiest part, and that is why our results are so weak. So for example, for imaginary quadratic fields, infinitely many have Polya group 1. So although their class, so in other words, the huge part of their class group comes from non-ramified primes. And that's a harder problem. So Polya groups are rather easy to handle, and in that respect, they are rather weak. The results cannot prove much about the class number 1 or 2 or 3 problems. The reason is that for class number 3, in order to effectively compute the list, for example, we had to find a good bound for the discriminant. And good bounds for discriminants are usually done with Riemann hypothesis or GRH or stuff like that. So whenever you have an unconditional result about Ziegel zeros, then you have an unconditional result about some bounds on discriminants. And that's why I didn't want Farahnaz to tackle those problems, because I guess anything related to Riemann hypothesis is really difficult. And what she has done is that she has found that there has been a good recent work on good bounds for Siegel zeros, and she's using that to kind of give a reasonable to find a reasonable bound on the discriminant to be able to compute the whole list, I hope. We haven't completed the computation. This bound that she has found is rather huge, but we think it's doable in IPM's computer cluster.
So when you say results about Siegel zeros, do you just mean zero free regions, or you need more control on the Siegel zeros?
That's exactly zero free region. Yeah.
Okay. Are there any further questions? Okay, if not, then I'd like to thank Ali Rajaei again for the very nice talk.
Thank you. Actually, I don't deserve this. I should apologize for wasting your time.
I found it very interesting.
Kamal is in the audience.